Hello everybody. So we are going to solve this example here just to get more practice on the dealing with the tables and extracting data and doing the integrations for calculating the enthalpy and the internal energy. For this example, we have a gas that we assume it's an ideal gas. We want to calculate the heat that must be transferred for each one of the cases. The first case, we have a stream of nitrogen that flows at a rate of 100 moles per minute, and it's heated from 20 degrees Celsius to 100 degrees Celsius. The second is nitrogen contained in 5-liter flask. It was initially at 3 bars, and it's cooled from 90 degrees to 30 degrees Celsius. So what we want to calculate now is just the amount of heat that needs to be transferred in or out of the of this system. So the main difference between the two cases is the type of system. The first is a system where there is mass going in and out, so it's an open system. The second is a closed flask, and it is so it's a closed system. So in this case we will deal with the enthalpy. Here we will deal with internal energy. So this is the main difference between these two cases. For the first case, we don't have any information about kinetic and potential energies, so we will assume that the changes are zero, and of course there is no work. It's a heater, so the work is 0. So the equation will end up to be delta H dot equals Q. And we need to calculate the change in enthalpy. So change in enthalpy is equal to the molar flow rate multiplied by the change in enthalpies, or specific enthalpies, which is H2 hat minus H1 hat. So if we know H2 hat and H1 hat, or minus H1 hat, then we're done. We know already the mass flow rate, or the molar flow rate, which is 100 moles per minute. So the only missing part is the difference in enthalpy or specific enthalpies. So to do this, we will simply do the integration. We need to get the constants from the table. This is a nitrogen, and it's a gas because it assumes ideal gas behavior. So I cropped the part of interest here just to make it easy for us. This number is not going to be clear, the last part. So yeah, for now we already have the information that we have for A, B, and C. Just a couple of things. First, this is gas phase, so this is suitable to the conditions that we have. It says form number 1, so we are going to use the first form of the equation. The temperatures are in Celsius, so we will substitute with Celsius here. These are just some few things. So to get the enthalpy change from 20 to 100 degrees Celsius, it's going to be the integration of Cp dt from T1 to T2, which is 20 to 100. Just a reminder that the numbers here would be multiplied by 10 power minus 3 or power minus the power that we have here. So it's 29 times 10 power minus 3. This is 0.2199 times 10 power minus 5, and so on for the rest of the numbers. The rest is just integration and substitution. So after the integration and substitution, this is going to be 100 minus 20. This is 100 power 2 minus 20 power 2. This is 103 power 3 minus 20 power 3, and so on. So it's very, very straightforward. It's kind of long calculation, but it's not difficult. It's just time consuming. So delta H is going to be, of course, in kilojoules per mole, because these are the units that we have here, kilojoules per mole Celsius. Now we multiplied by Celsius, it's going to be kilojoules per mole. And finally, we can calculate Q as N multiplied by delta H, and this is what we are going to get in kilojoules per minute, based on the units that we have. So this is the first part. The second part is for the closed system. So the equation is going to be the closed system equation. Just one thing to quickly notice here, that we don't have the number of moles. In the first part, we already have the molar flow rate. The second part, we don't have anything. We have the volume, we have the pressure, we have the temperatures from 90 to 30. So we can use this information to calculate the number of moles using the ideal gas law, because the ideal gas law states that PV equals nRT, so we can calculate N equals PV over RT. It's important to notice the units, and this is why I did the unit conversions here. I put the liter into meter cubes, the pressure into Pascal, converted the temperature, or these temperatures are in Celsius as they are. So I put this in Pascal meter cube over 8.314 Pascal meter cubes per mole Kelvin. So the numerator has to be in Pascal meter cube to match the units that we have here. And this is the temperature. Of course, I used the 3 bars because it was initially at 90. So I put the 90 plus 273 to be in Kelvin, corresponding to the pressure at 3 bars. I don't know what is the pressure after it cools down. I can calculate it, of course, but I don't know what is the pressure. So the numbers that I must use are the numbers that correspond to the same state. So this is the number of moles. Now the rest is going to be the same. The equation will end up to be delta U equals Q, and delta U equals the N multiplied by U2 hat minus U1 hat, and this is the integration of CV dt from T1 to T2, and we know CV equals Cp minus R because it's an ideal gas. And we know that this is 8.314 joules per mole Kelvin, and we know the units of enthalpy are in or the constants are going to be kilojoules per mole Kelvin or Celsius. So joules and kilojoules cannot be subtracted, so I have to convert this into kilojoules. So I multiplied it by 10 power minus 3 to unify the units of the two terms, and then the rest is going to be the same as before. So by doing this, we can do the substitution, we can do the calculations, and finally you can get the change in specific enthalpy. We multiply it by the number of moles, and we can get the Q in kilojoules. So this is simply how we can solve the problem. So again, if you know how to pick the numbers correctly from the table, if you know how to do the integration and to substitute correctly, then it's going to be a piece of cake for you. One last thing that I want to mention here, which is something that we might and haven't mentioned for some time. We said that in cases like the cases that we just solved, we have two states, state 1 and state 2, and we need to get the difference. And we said that we must have a reference state in order to calculate this. But if you go back to the first part, we didn't mention anything about the reference state. We directly did the integration from T1 to T2. And for the second case, we had the integration from T1 to T2. We didn't mention anything about the reference state here. What we should be doing is to do the integration from T reference to T2 of Cp dt minus T reference to T1 of Cp dt. This is what we should do. And if you think about it, you would notice that we already done this. The way we did is, without mentioning, we took T1 as the reference state. And if you take T1 as the reference state, the substitute with T1 instead of each one of these T references, this is going to be 0. So this is my reference state. The enthalpy at state 1 is 0. So this is what we can see from this integration. Integration from T1 to T1 is 0, and then the equation will end up to be the integral of Cp dt from T1 to T2, which we already did. So by doing this, we are setting the initial state as the reference state without mentioning that. Of course, you can take any other reference state, and for example, for the first part of the problem that we solved it from 20 to 100, you can take the reference state, for example, 0 degrees Celsius. You can take it 50 degrees Celsius. You can take it anything. But what you will be doing is you will be doing the calculations for the integration and substitution twice, which would be a very time-consuming thing. We saw how long this process is and how much time it takes to do the integration, substitution, and calculation. So if you take another reference state, you are doubling the time that you are using to calculate delta H, and you're going to have the same output at the end. So there is no point of doing this. So it's more smarter to take T1 as the reference state, or there is another option, which is taking T2 as the reference state. If you take T2 as the reference state, this is going to be the case. It's from T2 to T2 minus from T2 to T1. And in this case, this is 0, and the equation would be negative the integration of Cp dt from T2 to T1. If you take this negative into the integration, put it inside the integration, then it's going to be the integral of Cp dt from T1 to T2, which is the same shape as this. So it's going to be the same thing. So it doesn't matter which one you take, T1 or T2, the output is going to be the same in all the cases. So this is a very important thing I wanted to mention, just to remind you that this is one of the basic concepts that we are following, even if we don't mention it explicitly. This is something we do all the time. Next time we will solve a couple more or one more example, and we will go through more details about the mixtures and how to deal with them. So we'll see you then, inshallah. Goodbye.